USDA ARS. And he's going to be talking to us about addressing soil test phosphorus recommendations. And just before he starts, someone left a phone over on that side of the room. So if you hear of anyone who lost their phone, we'll have it in the back in this room, and we'll keep it here a little longer. Okay.
All right, thank you, Jessica. All right, we'll talk about soil test phosphorus recommendations. And why do we care about soil test phosphorus recommendations? To get right to the point, we want to have, it's to our advantage to have very precise phosphorus recommendations for two main reasons. It will increase efficiency, agronomic production efficiency. You don't want to be applying too little. You don't want to be applying too much. Either one is an economic waste. And second, if you're applying too much, that can contribute to non-point losses of phosphorus. So we have a lot of incentive, both environmentally and economically, agronomically, to improve our soil test phosphorus recommendations. So if we consider the state-of-the-art system, what we have right now as far as phosphorus recommendations applications go, if you consider we've got zone management. This pointer show up here not too well. Okay, we have zone management. Your field broken up in different sections based on different differences in soils, different observed behavior, and so you often soil sample those zones separately and get your soil test report on it, and based on the soil test recommendations, you get a phosphorus application rate, which then through precision application, you can apply those custom tailored phosphorus applications to each zone. That's state of the art right now. But if in any link in this system, something is not correct, then you no longer have precise application. So in other words, if your phosphorus application rates are not correct, then essentially what you have is you have a precision application system that is precisely applying incorrect amounts of phosphorus. In other words, it's not really a precision application anymore. And that's what I want to talk about, is that part, the phosphorus application rates. So before we have this discussion, we need to discuss a little bit about how plants take up phosphorus and the dynamic with the soil. So I use the term effective bioavailability. So effective bioavailability of nutrients essentially considers that the nutrient must be in the proper form for uptake by the plant. It has to be in proper chemical form. The nutrient must be in solution. This is for all nutrients, but we're going to focus on phosphorus. The nutrient must be in solution, and the nutrient must be located in the vicinity of the plant root at the time of uptake. That's very, very important for phosphorus especially. Not nearly as important for nitrogen. So keep in mind throughout this whole discussion, plants take up nutrients from the solution. Plants do not take up nutrients from the soil. The soil feeds the solution. Here's how it looks if we try and illustrate it a couple different ways. In the soil, you have your phosphorus. We just very broadly categorize it into a couple different pools. You've got your soil-bound phosphorus. Within that, we can break that up into the labile pool, the non-labile pool. That's the phosphorus that's held very tight, the phosphorus that's not held as tight, and they're in equilibrium with each other. And that labile pool is in equilibrium with the solution pool. So it slowly releases phosphorus to the solution so that the plant can then grab it out of solution, take it up. Same thing showed in a picture here. You've got your soil solids, organic matter, inorganic minerals. Phosphorus and other nutrients are bound to it. They desorb into the solution, and once in solution, the plant can take it up. And it's that concentration of phosphorus in solution is ultimately what controls plant uptake of phosphorus and yield with regard to phosphorus at least. So this is an example of some corn yield data as a function of phosphorus concentration in solution. The thing about this is that it's universal. Right? It doesn't matter what your soil type is. It doesn't matter soil conditions. Plant roots see the phosphorus that's in solution. That's what controls it. That's why it's universal. There's two different soil. You probably can't see any of these slides at all. I don't even know why I bother turning around and pointing at them. There's two different soil types plotted up there, but they all fall on the exact same line. The solution phosphorus concentrations with regard to plant response, it's universal. It doesn't matter what the soil type is, doesn't matter where it is. Second thing we need to keep in mind as we have this discussion on phosphorus fertility recommendations is that the notion of phosphorus adsorption onto soil. It is very different from other nutrients that it's extremely strong. All right, so most of what you apply, phosphorus that you apply, binds very strong to the soil, and most of it, it's not coming off. So because of that, phosphorus is, it's mostly immobile. It's mostly immobile. Okay, so when we consider uptake of phosphorus in solution by plants, it is a function of obviously the solution phosphorus concentration. The higher the concentration of the phosphorus in solution, the easier it is for the plant to be able to take it up. But it also requires the ability of the soil, which holds the storehouse of phosphorus, to keep replenishing that solution. We call that the quantity. The phosphorus that's then supplied into the solution, once it's in solution, we call that the intensity. And you'll see, I'll use those terms a lot, quantity and intensity, that's what I'm referring to. And we need to keep in mind there's three methods of obtaining, three methods that plants can uptake solution phosphorus. All three of those methods or means of uptake are dependent on root architecture and the location of phosphorus being near the roots. Because phosphorus is so immobile, it has to be near the roots for plants to get up. That's why we ban phosphorus often. And those three means of plants taking up phosphorus is root intercept, any nutrient for that matter, root interception. Basically, the root runs right through it, and directly in the vicinity, everything it goes through, it can take up that phosphorus in solution. Bulk flow, which is as the plant's just taking up water, whatever happens to be in solution, it's taking it up. And the last one is diffusion. Diffusion is the most important, is the most critical means of uptake of phosphorus by plants. Brief illustration of diffusion. Imagine you've got start out with a soil where the phosphorus is evenly distributed throughout it. The plant begins to take up phosphorus from the solution, and it depletes it directly in the vicinity around the plant roots. And it creates a gradient, a concentration gradient, where around the root you have lower peak concentrations, higher peak concentrations away from the root, so the phosphorus moves by diffusion through that gradient back towards the root. Now, obviously, this diagram, it's not to scale. It's exaggerated here just to make the point. It's the dominant mechanism, but it's extremely slow and it's short range. It's only going to move around 1/4 of an inch. So, different plants take up phosphorus from the solution, and different plants require different concentrations in solution to reach their maximum yield. This is known as the external phosphorus requirement, and this is the list of textbook list of solution peak concentrations required to meet 95% of yield for different plants. Corns, they have listed about 0.025 milligrams per liter in solution. Beans at about 0.2. Talk more about that later. Okay, so that's great. All right, we have some idea of how much phosphorus is required in solution, but we don't measure what's in solution, right? We measure what's on the soil. So what's our soil phosphorus requirement? What is it a function of? Well, the soil phosphorus requirement, it's a function of the solution P requirement, or the external phosphorus requirement. So, like I said, we don't measure solution P. We don't the intensity, in other words. We don't mention that. We don't measure that. We measure what's in the soil. But the soil P requirement is dependent upon. It's partly a function of that. So, how do we know how much soil-bound phosphorus we need? Well, first of all, it depends on the external solution P requirement for that plant, and it depends on the ability of the soil to keep resupplying that solution. In other words, it depends on the quantity-intensity relationship for that soil, which is a measurement of the ability of that soil, again, to just keep replenishing that solution with phosphorus. And that quantity-intensity relationship is a function of soil properties, mineralogy, texture, organic matter, pH, Also, total phosphorus, obviously the amount of phosphorus in the soil is going to make some difference, right? And the chemical form of that phosphorus. Here's an example of a quantity-intensity relationship. Probably can't see it real well. But on the y-axis, you've got the amount of phosphorus held on the soil. And on the x-axis, you have the amount of phosphorus in solution. And notice very different relationships depending on your soil. There's a lot of different soils there with very different mineralogy. Just because you have 200 milligrams per kilogram of phosphorus on your soil, or 800 or whatever it is up there, doesn't mean you're going to have the same amount of phosphorus in solution for every soil. It depends on the soil properties. So how do we make how do we determine what our soil phosphorus requirement is? This is traditionally how it's been done. It's calibrated when you take your soil samples, send them into the lab at the university. They apply these sorts of recommendations to them based on this relationship. What you have here is your soil test phosphorus level on the x-axis, and it can be whatever it happens to be for your area. Bray, Malick 3, Olson, Malick 1, depends on where you're at. And we have yield on the y-axis. So we have yield as a function of soil test phosphorus level. Obviously, as soil test phosphorus level increases, we get greater yield, right? Until at some point you hit a plateau. All right, and where that plateau is, we call that the critical level. That's your target soil phosphorus level. That's where you want to be. All right, so this is how it's always shown, but in reality, if you ever look at the data for how these were produced, it looks like that. In fact, I'm being generous here. It's usually a bigger shotgun blast than that. So what they strike is basically an average of all soils, soil types, all conditions. But in reality, if you start breaking it up based on soil type and conditions, your line could look like this for your field. Might look like that. Could look like this. But that's not what you get. You basically get the average is what's used in making your recommendation. So it's possible, in many situations, you could be over-applying phosphorus for your particular soil and needs, or you could be under-applying phosphorus. It goes both ways. Either way, it represents an inefficiency in the system and economically. As an example, some real data. 3 soils illustrating differences in the critical level for as a function of clay content. So again, we have yield on the y-axis, yield as a function of soil test phosphorus. This is Malick 1. This is from North Carolina. And in the first example, the high clay soil critical level is around 9 pounds per acre. Again, this is Malick 1, so if you're thinking Malick 3, don't be shocked. 9 pounds per acre is what you need to hit maximum yield in that first soil. Second soil, critical level is 18 pounds per acre. Third one, 27 pounds per acre. So it varies not only as a function of texture, mineralogy, pH is a big one. I can't go through, I don't have time to go through how all the soil properties are going to affect this, but just mention some of the big ones here. Soil pH, right? We don't want our soils to be too acid or too alkaline. In acid soils, our phosphorus gets bound up. You can have it there. You can have a nice high amount of phosphorus in the soil, but it's not necessarily available. In acid soils, what happens? It precipitates out as aluminum iron phosphates, absorbs onto the surface of aluminum hydroxide iron minerals, making it unavailable. It's not soluble. In alkaline soils, it precipitates as calcium phosphate. Solid, not in solution. Remember, plants take up the phosphorus from solution. You got to be able to get it to come from the soil solids to the solution in order for the plant to get it. So because of that, the recommendations for ideal pH for phosphorus availability between 6, 6.7. That's your sweet spot. Do our soil test recommendations take this into account? No. Give me an example of this, some data. This is water-soluble phosphorus. This is a soil that has the total amount of phosphorus is exactly the same. We have variable pH. Vary the pH and we measure the amount of water-soluble phosphorus. So water-soluble phosphorus is essentially, you can think of it as something that represents the amount of phosphorus that will be in solution for the plant. And fits just what we said. Low pH that phosphorus gets tied up as iron aluminum phosphates, insoluble, increase the pH, and you get higher solubility, getting somewhere around pH 6 to 7. Okay, perfect. So those same soils, let's look at Malic 3. Here's Malic 3, exact same soils. So if you looked at this, if you didn't know any better, you'd look at it and you'd say, well, it looks like my phosphorus is more available at acid pH. But does that make sense? We know that's not true. We know that's absolutely not true. Soil test phosphorus levels can be very misleading without knowing other soil properties. Using them alone can be very misleading. Here's an example of a manifestation of that. This is the soil. This is winter wheat data from when I was in Oklahoma. This is a field that had Malic 3 phosphorus levels of 5 milligrams per kilogram, very low. It required soil test recommendation required application of 83, approximately 83, we'll call it pounds per acre, close enough, of P2O5. And so we applied that. We applied in the black bar, you can see the 83 pounds per acre of P2O5, and then we also applied 0. And then we also applied everything all the way up to 112 pounds per acre. No significant differences in yield. Here was a soil with very low phosphorus. Why is there no response? There should be an increase in yield. Why not? No significant differences. It didn't matter if we had a 0 or 112 pounds per acre. Why? I don't know. It's probably not soluble. Yeah. That's the control. Okay, so we have a soil phosphorus requirement. That's your target, what you want the soil levels to end up being, because the soil feeds the solution. So what's our fertilizer requirement going to be to feed the soil, to get the soil up to those levels, so the soil can feed the solution, which feeds the plant, right? So your fertilizer phosphorus requirement is a function of, well, what's your target? What's your soil phosphorus requirement? Your quantity that you want that you want it to be. And it's also a function of the fertilizer phosphorus, soil phosphorus addition. In other words, not all soils respond the same to fertilizer addition. You can add 100 pounds per acre phosphorus to one soil and you'll increase your Malic 3 levels to, you increase it a certain amount and add that same 100 pounds per acre to another soil and you won't increase it as much, or you'll increase it much, much more. So this fertilizer-soil P relationships vary between soils as a function of soil properties and the conditions. So ideally, if we show this, try to illustrate everything I've just said into a single diagram. You can't see this, at the top, our fertilizer rate recommendation is ultimately what we're after. We want to know how much phosphorus do we need to apply. That's the bottom line, right? Well, ideally, if we had all the information at hand, we know it's a function of the soil phosphorus requirement. What's the soil phosphorus level need to be? And what's the what's the fertilizer phosphorus soil P relationship? How much will an increment addition of phosphorus increase the soil test level? All right, well, we can't stop there. The soil phosphorus requirement, that's a function of three things. That's a function of the quantity-intensity relationship, that is the ability of that soil to supply phosphorus to solution. It's also a function of your solution P requirement. What concentration does the plant want in solution to be happy? And where is that phosphorus located? Is it evenly distributed throughout the profile? Is it going to be near the roots? Because phosphorus isn't moving to the roots. It's not like nitrogen, where the plant just starts sucking up water and all that nitrogen's going with it. Phosphorus doesn't work that way. And those are going to be a function of soil properties and management. And your external phosphorus requirement solution is going to be a function of crop type, because corn needs a different concentration solution than beans versus wheat or whatever. So currently, we don't consider all that, right? Currently, our routine testing does not measure solution P intensity, and I understand why. That it wouldn't make sense. You go out and measure it one day, it could be different the next day. Instead, we use extractable soil phosphorus. Your Malic 3s, Malic 1s, Brays, Olsons, Morgan, and they were designed, brilliantly designed, I might add, in order to create an index value of phosphorus that is related to both the quantity and the intensity of phosphorus in that soil. In other words, the extractable soil test phosphorus is related both to the solution P concentrations and the ability of that soil to keep replenishing it throughout the growing season. And they work fairly well for that, but they can be more precise. Or another, I should say, a better way to put it is we can use them better. We can use them more wisely. So because of that, because it's an indicator of that, it ends up becoming, we get a good correlation between your soil test P and yield. So one of the problems is that our fertilizer recommendations are somewhat outdated. They're based on soil test results that are 0 to 6 inches, which isn't representative of no-till conditions, where a lot of the phosphorus is often stratified in the top 2 inches. Remember what I talked about how phosphorus moves through the soil and how it doesn't move through the soil very well, a tiny bit through diffusion. So location is really important. If you're taking a 0 to 6 inch sample, that might not cut it. It's also based on calibrations conducted 30 to 50 years ago with no consideration for soil type or conditions. Doesn't consider pH or anything like that. Doesn't consider mineralogy, texture. We know that affects it. We demonstrate that. Also, we have different crop varieties now. So the demand is different, or potentially different. Something needs to be determined. So if we take our idealized system for making informed fertilizer recommendations and compare it to what we have. All right, well, we do sort of consider quantity, intensity through the soil test extract. It's sort of an index of both of them. It's empirical, but it does somewhat consider, but it doesn't take into account soil properties. We don't consider P location and the ability of it to move through the soil to the root. So therefore, we don't consider soil properties management for that. We do consider the fertilizer soil P relationship very generically, but we don't consider the impact of soil properties and management on that as well. And we sort of consider solution external P requirement, so somewhat indirectly, but not really. So this is what our current approach to soil phosphorus testing looks like compared to the ideal. So it's okay, but it's empirical and it's somewhat uninformed, and we can do better with it. I'll give you an example of a manifestation of this. These are some phosphorus strips we applied in northern Indiana. And these were some sites. We cherry-picked these sites. We didn't randomly pick these fields. These were fields that the farmer indicated himself that he said, hey, I got these soils. They're pretty low testing soils, but everything's always fine. I always get a fine yield from it. They never really seem to respond to phosphorus fertilizer. So I don't have to add much to them, or hardly ever. So he said, let's put some phosphorus strips out there and compare it versus the rest of the field, which did not receive any extra phosphorus. And so, probably can't see it very well from there, but you can see outlined are the phosphorus strips. And if there was a yield response, you'd see a stark difference in color within those strips versus outside of the strips. And you don't. In other words, there's not really a response of phosphorus in these soils for yield, but they should, based on the soil test, they should. Why not? So, where do we start for improving our soil test phosphorus recommendations to make them, we want to make them more precise. Where do we start? So, this is where I'm starting. This is where I propose we start. At the very basic level, right here. How much phosphorus is required in solution for the plant to be happy? What needs to be in solution for the plant to be happy? What concentration in solution? From there, we work backwards and then study the ability of different soils and how their properties affect their ability to supply that solution to the soil, with working with quantity, intensity, and how it's impacted by soil properties. That's the approach we're taking. That's where we've started. Our current phosphorus recommendations, I'll say that they're not bad. They're definitely not bad. They get us in the ballpark, and they served us very well for many, many decades. And it was fine. But now we have greater economic concerns and environmental concerns that we now have this incentive for making them more precise. They get us in the ballpark, but they're not precise. Therefore, there's lots of room for improvement. This improvement would definitely save money. I mean, if you only had to increase your soil test P level by 10 milligrams per kilogram instead of 20, and we're talking, if you're using MAP as your phosphorus source, we're talking savings of around $30 per acre. It's no small amount. We would additionally improve, more precise recommendations would improve production efficiency and potentially reduce phosphorus losses. So here's where I'm starting right now. I'm going to determine those critical concentrations in solution for the plant. So this is the approach we're taking. I'm using a sand solution, or it's a hydroponics approach. It's considered a sand culture. So I'm using a sand as a physical medium for growing the plant, but the sand is 100% inert. It won't absorb phosphorus or any nutrients for that matter, and it won't absorb nutrients, it won't desorb them. So whatever I apply in my nutrient solution is exactly what the plant sees. I can control the nutrient concentrations very, very precisely. And so that's what we did. We grew our plants. We started with corn and beans as a preliminary experiment last summer. And we varied, we applied, supplied all the necessary plant nutrients in adequate amounts except for phosphorus. Phosphorus, we varied the concentration from 0.01 milligrams per liter up to 0.35. And the idea was when we hit the optimum concentration, our yield will plateau, right? Very simple. Here's what our corn looked like. This is corn at 0.2 milligrams per liter. The textbooks say 0.02 is all I need to get optimum yield for corn. There's 0.2. It looks terrible. It was showing deficiencies of magnesium, potassium. They looked terrible. In fact, I don't think they made it much past 6-7 weeks. What's going on here? We thought, man, do we have root diseases? What was happening here? It wasn't the other nutrients. We checked the other nutrients, no deficiencies in our solutions. It was fine. Was it oxygen? We thought maybe it was a lack of oxygen. Certainly couldn't be the phosphorus, right? The textbook said 0.02. We got 0.2. That's 10 times more than what we need. It should be fine. So we did a quick test just in case. And we did a quick test where we supplied supplied phosphorus at 15 parts per million, where we knew would be well over whatever the corn wanted. And we compared it to about 0.3 parts per million, which should be adequate, with and without oxygen. And you can see very clearly, 15 parts per million on the left. We were limited by phosphorus when we only had 0.2, 0.3 parts per million. So in other words, the textbooks are wrong. Everything you see in this table, wrong. They said corn, 0.025 parts per million. That's all I need. Wrong. Soybeans, 0.2. We did soybeans too. Not true for soybeans either. How are they wrong? If you go back and look, this work was done mostly in the 60s and the 70s. The methodology they used for measuring the solution P concentration, there were flaws in that, and specifically they used soils. I'm not using soils. I can much more precisely control my concentration, so I'm not going to get into details of that. Another thing we learned on the way, again, we're in the infancy of this research. You ever see phosphorus deficiency on soybean? People say you can't see phosphorus deficiency on soybean. You look at most of the extension documents and they just say, well, you have lower yield. Well, okay, obviously. They say there's no visible deficiency other than less yield. Here's what it looks like. Here's your trifolds. It looks very similar to a potassium deficiency. These trifolds are taken 24 hours apart. The burning pattern is different from potassium deficiency, but 24 hours apart, and after that last picture, next day, it fell right off. Phosphorus being mobile in the plant, the deficiency appears on the older leaves. We saw that in all of our treatments. Remember, soybean was supposed to be adequate at 0.2 milligrams per liter. We added up to 0.35. We should have had no problem reaching our optimum yield. You can see that's our pod mass per plant. Here we have 0.35 as the highest. Does it look like that's even coming near a plateau on yield? Not even close. We're still highly linear. So soybeans, much too low. What can I tell you about corn? What's the solution concentration threshold? I think it's less than 15 parts per million. It's more than 0.2. Soybean, I know it's more than 0.35. That's all I can tell you right now. And this is something we are We are working, that's the beginning step of working backwards, and this is going to take years. I don't see, soil, I want to quickly say that I don't see soil phosphorus tests going away. We need them, but we need to use them better. Any questions? Yes, sir.
In your study of the phosphorus in the inert material, when are you adding phosphorus? Is that from time of germination all the way through?
Yes. 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 And it's amazing how much phosphorus is in a seed. The soybeans at the really low concentration, our lowest was 0.01 parts per million. That's detection limit on most equipment. And yet, it still grew. It didn't produce any pods, but you know, it grew a bunch of leaves. Some of them at very low, like 0.03, 0.05, it still produced 1 or 2, 3 pods per plant. That's amazing. But we applied the nutrient solution several times a day. So it always had the exact same concentration in solution 24/7. We have any time for more questions, or I cut it?
One question up front, that'll be our last
yes, sir.
question.
You had a slide where you showed like you had applied 15 ppm parts per million and the
Yes, sir.
what was the question? Yeah, that one.
The-
Right. So
I'll repeat it in a second. Go ahead.
what about other nutrients? Like, you know, did you change nutrient concentrations in other nutrient concentrations?
Okay.
in
In
those?
this slide, where all the plants are receiving the exact same concentrations of all plant nutrients except phosphorus. So the idea was we're adequate for everything.
So did you use the book values for the other nutrients, or how much?
I used that it took a long time just to figure out what concentrations to use. I didn't want to use, most people in horticulture, they use what's called the Hoagland solution, but that is big time overkill, way too much. So I spent a lot of time in the literature coming up with the best solution. So a lot of it ends up being mostly a quarter of the Hoagland concentration. Works just fine, and it's still more than you need. I just wanted to make sure I wasn't deficient or toxic in anything that I added. And then I could vary the phosphorus concentrations.
Okay, I was just curious. Yeah.
Okay, that's it for now. If you have another question after we're going to lunch. So thank you for your time. Thank you for everyone in this session. We'll be back here at 12:45.
Like B200.